Welcome to Sift Tutorials. In this video we will look at how to identify curtailments. Most turbines have many different operational modes, including, for example, noise reduction modes and curtailment. We define curtailments as periods when the turbine is actively reducing its output. There are many reasons for curtailments. For instance, requests from the grid to reduce site output or an automatic output reduction when high component temperatures are measured. In this power curve, we can clearly see some curtailments as horizontal lines. For these curtailments, turbine output power is simply capped. This is generally achieved by early blade pitch action, which is clearly visible in the pitch versus power plot. Let's have a look at this. We need a new flag for this. Let's open the project overview and create a new flag. This flag should be of type derated. As we are looking to highlight a horizontal line in a scatter plot, we will use a search rule. Let's have a look at search rule settings. We need a rule that will assess the rate of change of one signal compared to another one. dydx allows us to do that by computing the backwards finite difference, an approximation of the first order derivative. This allows us to select points where one signal changes very little, while another changes at a much higher rate. It is calculated by taking the difference between consecutive samples for both the numerator and denominator, then dividing. This allows us to select points with one signal's rate of change with respect to another signal's rate of change. For example, here we are interested in periods where pitch changes whilst power is relatively constant. Other search types are explained in the user guide. This rule will categorize all horizontal lines on the power versus pitch curve as curtailments. However, some are normal operation. The search rule filter string can be used to limit the search. Points at zero power can be a mix of normal operation at low wind speeds and curtailment to zero power at high wind speeds. To differentiate between the two, we use generator speed. As the wind picks up, generator speed increases. When generator speed reaches a certain value called the cut-in generator speed, the turbine starts being able to produce power. We will use the cut-in generator speed at this turbine to differentiate idling and curtailment. This value is easily identifiable from the power versus generator speed plot. To do this, let's zoom into the X value where we see Y values start to increase. Points at rated power can be excluded by filtering out points above 95% of rated power. The control strategy limiting turbine output power to rated power is the same one that is used to limit production to lower power levels. Therefore, there is no clear operational signal to differentiate curtailment and rated power control. For the analysis, this means that curtailments at levels higher than 95% of rated power will not be classified as a curtailment, but as a change in rated power. The lower and upper bound allows us to set which values of the estimated derivative should be flagged. For power versus pitch, a good rule of thumb is to use plus and minus 1/100th of the rated power. In this case, this results in a limit of 20 kilowatts change in power for every 1 degree change in pitch angle. The threshold sets the minimum number of consecutive points where the derivative falls within these lower and upper bounds. We set it to 3 to require at least half an hour in this mode, reducing the number of false positives. The other settings can be set to 0 and the flag can be applied. Not all curtailments have been flagged. We know from our previous tutorial on downtime flagging that there is no pitch data before 2019, so pitch-based rules will also miss any curtailments in that period. We can set up a second search rule on power versus wind speed for the period where no pitch data was available. As with downtime flagging, wind speed based rules are less accurate. The bounds we set for the second flag rule are plus and minus 25 kilowatt change in power for every 1 meter per second change in wind speed. We set a 6-point minimum for the threshold to be a bit more conservative and reduce false positives. When we reapplied the flag rule, we can see all curtailments have been classified. The search rule also picked up on an otherwise difficult to see curtailment around 600 kilowatts. We have introduced different ways to flag curtailment in downtime. You can see the power curve is not perfectly cleaned yet. Feel free to explore the data and see if you can come up with rules to further improve flagging. In the next video, we will use the clean data to define baseline turbine performance.